Welcome to our final new section of the year. This is the last new content that I need to teach you before you finish your time in honors pre-calculus. Um, let's go ahead and jump right in. Let's talk about some applications of vectors. We have one learning target for this section, and that's basically to be able to solve these different types of word problems, these real-world applications. So I'm just going to jump in. There's a lot of applications for vectors, mostly in physics, but we're going to see a bit of a variety here. So we're obviously not going to get to explore every application of vectors, but we're going to look at a few major ones. We're going to start with velocity. So this is often phrased in terms of planes and headings and crosswinds and finding the velocity of planes because of the crosswinds and things like that. So let's jump right in. So an airplane heads due north at 300 miles per hour. It experiences a 40 mile per hour crosswind flowing in a direction of 60 degrees northeast. So I didn't catch this before I finished printing and getting all of these guided notes ready for you, but um, I would rather give you that 60 degrees northeast as a heading like we've been using. So that would be the same thing as north 30 degrees east. All right. 60 degrees in a northeast direction. It's the same as north 30 degrees east, just to keep things clear for us, nice and clear and consistent. So we are looking for the velocity of the plane relative to the air. So what that means is ignoring the impact of the air, or ignoring the impact of the crosswind, what is the velocity of the airplane? Well, that's pretty straightforward. They told us it's heading due north at 300 miles per hour. And for a lot of these problems, we're going to use our ij form. Remember that a vector v equals ai plus b times j. So in this case, it's heading north at 300 miles per hour. That means there is no horizontal component to this vector v. So a must be 0. And then b is 300. That's the magnitude or the speed in a vertical direction. Positive because it's going north. So that is the component form of the velocity of the plane relative to the air. We can also find the velocity u of the wind. So north 30 degrees east means the wind is about there. Okay. Now let's stop and take a second to figure out. We need to find we want this vertical component and this horizontal component of this vector u. Well, if this is a right angle, we have 30 degrees taken out already, so we know that angle is 60 degrees in the triangle. And I'm sorry, I know that's a really small picture. Promise it'll be a little more clear in class on the board. If you are just watching this video, you have questions, come talk to me. So u, we need to find a. Remember that a equals the component or the magnitude of the vector times the cosine of its direction, and then b is the magnitude of the vector times the sine of its direction. So ai means that I have the magnitude of this vector, which is 40 miles per hour, times the cosine of 60 degrees, which is its direction, and then 40 times the sine of 60 degrees. If I simplify that, I get 40 times 1/2, which is 20, and then 40 times square root of 3 over 2, which is 20 times the square root of 3. So that is vector u in component form. We found its horizontal and its vertical components. All right, so that is helpful to us because now our next question is find the true velocity of the airplane as a vector. In other words, we know the plane is traveling due north at 300 miles per hour, but there's this wind, and this wind is kind of pushing it a little. It's preventing it from traveling at exactly 300 miles per hour. It could be making it travel faster if part of this wind is pushing it along in the direction that it's traveling, or it might be slowing it down if it's any part of this crosswind is pushing against the plane. So we need to figure this out. Now to do that, we have this vector v, we have this vector u. Now the actual velocity of this plane is going to be whatever vector is formed when I consider the displacement that both of these vectors is causing. In other words, what is the sum of these two vectors? I know that's kind of a leap, but a lot of these problems require us to think like this. That's why I really want you to think about vectors as displacement. It makes a lot of these applications and real-world problems make a lot more sense. So we're looking for this vector here that's the sum of u plus v. And we'll just call this vector whatever you'd like. We can call it vector, I don't know, w, just so it's not any letter that we might be using otherwise. So w is going to be u plus v. Well, we have u and we have v. We just found that. So 20I plus 20 root 3j plus 0I plus 300j. So this vector w, or the true velocity of this airplane as a vector, is 20I plus 0I is 20I plus 20 root 3 plus 300j. And that's it. That is the true velocity of this airplane. So finally, bringing it full circle, part C is asking us what is the true speed and direction of this airplane. So we have the velocity as a vector of this plane, but we want the actual speed that this plane is traveling at and the actual direction it's traveling in. Well, speed is a scalar. True speed, then, is going to be the magnitude of the true velocity of the plane. So we need the magnitude of w. It's going to be the square root of 20 squared plus 20 root 3 plus 300 squared. Now please be extra careful as you're trying to solve this, putting it in your calculator or doing this by hand. I can't just distribute that square here and here. I cannot do that. Think of this as a binomial, so I would have to square this binomial, so I do think you should just plug this into a calculator in this case. And if we do that, we get that the magnitude of this vector, in other words, the true speed of this plane, is 335.24 miles per hour. So because this crosswind is kind of helping to push the plane along, in other words, part of this crosswind's vector has a component that's pushing along the direction of the plane, it's helping it speed a bit. So instead of only traveling at 300 miles per hour, it's traveling at 335.24 miles per hour. And in fact, this is exactly how we do calculate flight plans and flight paths. I always thought it was interesting traveling back and forth between here and where I went to school in Chicago, Northwestern. It takes almost an hour more to come here than it does to go from here to there. And that's because of the huge difference that the crosswinds make, especially when you're traveling across the country like that at such a big angle. That's a huge difference, and a huge difference on the speed of the plane. So we're not done though. I digress. We are also looking for the true direction of the airplane. In other words, we want that theta that tells us in standard position where is this plane traveling. All right, so let's think about this. We'll redraw the picture. So I want this theta. This here is the magnitude of that vector w. This is the horizontal and vertical components of the vector, which we found up here in part B. So this is 20. This is, if we plug that into a calculator and approximate it, it's about 334.64. So we could, since we know all three sides of this triangle, use just about any trig function to find the angle, but let's just throw it into tangent. Tangent's going to be opposite over adjacent, and then we need the inverse tangent of both sides to solve for the angle theta, and in degree mode, I get 86.58 degrees. So if I want to write this as a heading like I was given, then I need to subtract this from 90, right? Because if this is 86.58 degrees, that's like that. So if I want to write it as north a certain number of degrees east, subtract it from 90, that's north 3.42 degrees east. All right, there it is. So finding the velocity and the speed and direction of a plane. Actual, real application that's incredibly useful to us. Example 2 is a lot less involved, so I think I'm going to let you try this on your own, and of course we will cover this in class as well. But I'm going to move on to example 3, and that's talking about the heading, not just of a plane, but in this case of a boat. So a woman launches a boat from one shore of a straight river and wants to land at the point directly on the opposite shore. So let's suppose this is our river, and we're going from this point, and this woman wants to land her boat right here. She wants to go straight across. If the speed of the boat relative to the water, so again, we're ignoring movement of the water, is 10 miles per hour, and the river is flowing east at the rate of 5 miles per hour, in what direction should she head the boat in order to arrive at the desired landing point? So let's take a second and unpack that and think about what all of it means. There's this river flowing east, so we'll call this the river vector, r. And it's flowing at a rate of 5 miles per hour, so that magnitude of r is 5. And, that flow of the water is going to push the boat. So if I want to go straight across and I aim my boat straight across, the direction of the water is going to affect where I end up. I'm not going to go straight across. I'm going to end up somewhere over here. And we don't want to do that. So we should probably head our boat somewhere to the left a little from straight across. But we want to figure out exactly how much. So in other words, we should head our boat somewhere this way. Our actual, we'll call it the actual velocity, v. And the speed of the boat, in other words, the magnitude of that vector, is 10 miles per hour. All right. So let's start by writing these vectors in component form. We do want this angle here, this whole angle right here. So we need to figure out a way to find that. So vector r, it's only traveling horizontally, so it's going to have 0 vertical component. And it has a magnitude of 5, so 5i. Vector v, we know that we have the magnitude of vector v times the cosine of the angle, or of its direction, times I plus magnitude sine of the direction times j. So that's 10 cosine theta I plus 10 sine theta j. And then this vector straight across is the sum of v and r. Okay, and we can rearrange these vectors if you really want to see that, but if I'm trying to go straight across, the river's pushing me, we move vector v over and we see that it is, in fact, the sum of r and v. So w is r plus v. So it's going to be 5i plus 10 cosine theta I plus 10 sine theta j. In other words, 5 plus 10 cosine theta I plus 10 sine theta j. Now we want to go straight across. We want vector w to have no horizontal component whatsoever, only a vertical component. So we want this I to go away, and to do that we need its coefficient to be 0, the scalar we're multiplying it by. So we want 0i. So what that means is that we need 5 plus 10 cosine theta to equal 0. Look like a pretty simple equation, right? So 10 cosine theta equals negative 5. Cosine theta equals negative 5 over 10, which equals negative 1/2. Where does cosine equal negative 1/2? It's going to be 2 pi over 3. So that is where we should head this boat if we want to go straight across, based on the speed of our boat and the speed and direction of the flowing river. So, how useful is that? I don't know. You probably won't find yourself trying to sail a boat across a river, but it's certainly pretty cool that we can figure that out. And in fact, okay, some people do find themselves in these kinds of situations, especially engineers and planners and things like that, and this is how they figure these things out. You are getting a taste of what real math is used out there. All right, so that's it for heading. We can also talk about the force of a certain, I can't think today, I apologize. We can also talk about force and vectors related to force, direction, and magnitude of a force. So let's look at a quick example. A man is pushing his lawnmower with a force of 30 pounds exerted at an angle of 30 degrees to the ground. So there's man here, he's pushing his lawnmower down at an angle of 30 degrees to the ground. So here's the ground, here's the force, he's pushing it downward. And we want to find the horizontal and vertical components of this force. So we want to find this and this, B and A. Well, the magnitude of the force is 30 pounds. The horizontal component of this vector, A, is going to be the magnitude times the cosine of its direction, in this case 30 degrees. So, plugging in 15 root 3. And then the horizontal, or the vertical component, is the magnitude times the sine of 30 degrees. 30 times 1/2, which is 15. But here we do have to be careful. Okay, we do have to still check and make sure that makes sense. We are pushing in the left, or in a right or in a positive direction horizontally, but part of this force is also directed downward. So we have to make sure that this is negative 15 here. But basically that's it. We can break down this force that we're exerting into its horizontal and vertical components. And we're going to see in a second why that's so useful to us. Before we do, though, I want to go through one more force example. No, it's not just because I like Star Wars. A car weighing 3,000 pounds is parked on a driveway that is inclined 15 degrees to the horizontal, as shown in Figure 5. Well, obviously there's no Figure 5 here. I'm going to include that for you. So let me sketch that. So here's a driveway. It's inclined 15 degrees, and I've really exaggerated that 15 degrees, but that's okay. There's a car here. I don't know, I can't draw, so I'm going to draw car. Isn't that a lovely picture? It weighs 3,000 pounds. Okay, so going straight down, whatever this vector is, we'll call it the weight. I don't know, W. That weighs 3,000 pounds. So the magnitude of that vector is 3,000, and it's pointing straight down, because that's how gravity tends to work. And we want to find A, the magnitude of the force required to prevent the car from rolling down the driveway. So this car, of course, is trying to go down the driveway. And there's an equal force, there must be an equal force, that's pointing in the other direction, stopping it from rolling down the driveway. Now, since we're talking about a magnitude and not a direction, a scalar instead of a vector, we don't need to care about that direction. So we just need to find the magnitude of one of these vectors, and I think this first one is going to be a little easier. We'll call that vector u. Let's see here. It might help, sorry, I'm trying to think of how to explain this. It might help if we also look at part B, find the magnitude of the force experienced by the driveway due to the weight of the car. So in other words, the part of this force that's pointing straight into the driveway. I don't know, we'll call that V again, since we seem to like these 3 letters in this unit. Well, this angle in here is going to also be 15 degrees, because right here is a right triangle. This is 15, this is 90. That makes this 75. Okay. So let's go back to part A. Find the magnitude of the force required to prevent the car from rolling down the driveway. All right. So we need this right here. In other words, we want the component of this W vector, the weight of the car, along vector U. And I hope you see that. We want this component right here of this vector. So we know that from our component formulas, that component is going to be the magnitude of W times the cosine of the angle between those two vectors, which in this case is 75 degrees. Plug that into a calculator and we get about 776 pounds. So that's the magnitude of the force that's both pulling that car down the driveway and also the magnitude of the force that's pushing back and preventing it from rolling down the driveway. And that really all just came down to understanding the components and being able to see that. Now I will say that was a really tricky setup to this problem. On an exam, I probably wouldn't ask you for something quite that complex, but you never know. Part B, we want the magnitude of the force here. In other words, we want the component of vector W along here. Which again, from our formula for component of a vector along another vector is this. 3,000 times the cosine of 15 degrees here is the angle between those two vectors. And we get about 2,898 pounds. So that's the magnitude of the force that the driveway feels because of the weight of the car. There isn't a whole lot else to say about this problem. I know it was probably really weird and difficult for you to completely understand, but go ahead and pause. Think about what I'm saying when I say that this right here is the component of vector W along vector U, and then this here is the component of vector W, vector V. All right. Moving on, our final step here, we can talk about work. Now, in physics, work is formally defined as the force exerted on an object over a distance along a straight line. If the magnitude of that force is F and the distance is d, then the work is given by that simple equation, force times distance, F times d. This formula only works when the force vector is directed along the direction of motion. So in general, the only part of a force that affects an object is the component of that vector F in the direction of motion. We call that vector d. So the magnitude of the force on the object is the component of F along that direction of motion. So component formula. And if we plug that back into our work formula, force times distance, that's the force that the object feels, and then this is the distance. So if we move things around, the dot product just naturally shows up. So, very simply, the amount of work done by a force F in moving along a vector d is simply the dot product F dot d. And that's really nice. That's really useful because that's an incredibly straightforward formula that we can use. So let's go through these last two examples. A force is given by the vector F equal to 3 and moves an object from the point 13 to the point 59. Find the work done. Well, work is F dot d. We have vector F, but we need vector d. How do we get that? Well, here are 2 points, x1 and y1. x2, y2. We know how to find component form of a vector. That's 5 minus 1 and 9 minus 3, which equals 4, 6. So plugging that in, multiply the a's together, and then add the product of the b's, and we get 8 plus 18, which is 26. And if we're talking about the typical unit for work done, the force is in terms of pounds. The distance is usually in terms of feet. So the work done is with this weird unit called the foot-pound. As funny as that sounds. Those of you in physics will, I'm sure, be familiar with that. And that's really it. So we're not getting into super intense physics here. I just want a very nice introduction to how we might use these vectors in a variety of situations. I kind of want to leave example 7 to you because I think example 7 is a little more difficult, which makes it perfect for you to try to challenge yourself. And of course, we will go through it in class as well. Basically, that's it. So that was the final new section of our final unit, which means we're done. It's been a pleasure. It's been an honor. And we're going to start reviewing soon. Finish up this unit. So please put together a plan for any retakes you want to finish before the final, and prep for this unit exam. So let me know if you need anything. Otherwise, have a fantastic day.